Your sun is going to die. Not someday far away, but with absolute certainty written into physics itself. Most people imagine this a sudden catastrophe. The reality reveals something far more precise and inevitable. Tonight we're discovering exactly how scientists predict our sun's death, and why every step follows laws as reliable as gravity. Before we begin this cosmic countdown, drop a comment about what you think stellar death looks like. If you enjoy these explorations of our universe's most dramatic processes, consider subscribing. Ancient astronomers thought stars were immortal. They seemed unchanging across human lifetimes. Even early telescopes couldn't detect stellar evolution happening in real time. Everything changed when we learned to weigh stars. Scientists can measure how much matter each star contains. This measurement is called stellar mass. Mass determines everything about how a star lives and dies. Our sun weighs about 330,000 times more than Earth. This places it in the middle weight category of stars. Stars with this exact weight follow the same predictable life cycle every single time. Today, astronomers find thousands of sun-like stars at different life stages. Young stars just beginning to shine, middle-aged stars like ours, old stars approaching death. This creates a cosmic time lapse showing our sun's inevitable future. Astronomers point telescopes at similar stars throughout our galaxy. What they see reveals the complete story of stellar evolution. Each star represents a different chapter in the same book. Some stars appear young and hot. Others look middle-aged like our sun. Still others show signs of approaching death. Scientists can arrange these observations in order from birth to death. This technique works because stars of identical weight evolve identically. Physics laws operate the same way everywhere in the universe. A star exactly like our sun will always follow the same path, no matter where it exists. The evidence comes from direct observation of thousands of stars. We're literally watching our sun's future playing out in real time across the galaxy. Deep inside our sun's center lies its power source. Nuclear fusion converts hydrogen gas into helium gas every second. This process releases enormous energy that powers everything we know about life. Scientists can calculate exactly how much hydrogen fuel remains. The measurement shows our sun has burned through about half its nuclear supply. Roughly 5 billion years of fuel still remain in the tank. This calculation works with mathematical precision. Our sun converts 600 million tons of hydrogen into helium every second. At this exact rate, fuel depletion becomes completely predictable. Once the center runs out of hydrogen, our sun must find alternative energy sources to survive. This transition triggers the spectacular death sequence that transforms ordinary stars into cosmic monuments. Stars exist on something called the main sequence. This represents the stable phase when stars burn hydrogen in their centers. Our sun currently sits on this main sequence and has been there for billions of years. A star's position on the main sequence depends entirely on its mass. Heavier stars burn brighter and die faster. Lighter stars burn dimmer and live longer. Our sun sits perfectly in the middle range. The brightness-to-mass relationship follows precise mathematical rules. Scientists can look at any star's brightness and immediately calculate how long it will live. This relationship never varies anywhere in the universe. Our sun's main sequence position guarantees it will live for about 10 billion years total. We're currently about halfway through this lifespan. The stellar physics operates with clockwork reliability. Modern astronomy uses powerful computer simulations to model stellar evolution. These programs input a star's mass, composition, and age. They output the complete future evolution in precise detail. The simulations solve thousands of complex physics equations simultaneously. They track temperature changes, pressure variations, and nuclear reactions throughout the entire star. The calculations predict exactly when and how each phase of stellar death will occur. Computer models have been tested against real stellar observations for decades. The predictions match observed reality with stunning accuracy. Scientists can now forecast stellar evolution millions of years into the future. For our Sun, these models reveal the complete death sequence: shell burning, red giant expansion, helium flash planetary nebula formation, white dwarf cooling. Every stage follows predictable physics with precise timing. Nuclear fusion inside stars operates like a factory assembly line. Hydrogen atoms combine to form helium atoms. When hydrogen runs out, helium atoms combine to form carbon atoms. Each stage releases different amounts of energy. Our Sun currently runs on hydrogen fusion in its center. This process has remained stable for nearly 5 billion years. But hydrogen fuel cannot last forever in any star of our Sun's mass. When center hydrogen exhausts, the star switches to burning hydrogen in a shell around the dead center. Later it will ignite helium fusion in the core. Each transition follows the same sequence in every similar star. The nuclear assembly line determines the entire stellar death process. Scientists know exactly which elements will form and when. The sequence never varies for stars of identical mass. Our galaxy contains billions of stars at every possible stage of evolution. This creates a natural laboratory for studying stellar death. Scientists can observe the complete process by looking at different stars. Telescopes reveal young stars just beginning hydrogen fusion, middle-aged stars like our Sun burning steadily, old stars expanding into red giants, dying stars ejecting their outer layers, white dwarf remnants cooling slowly. Each observation provides another data point confirming the theoretical predictions. The galaxy serves as a living textbook showing every phase of stellar evolution happening simultaneously. Thousands of stars identical to our Sun exist at different evolutionary stages. This cosmic time lapse reveals our Sun's future with absolute certainty. We're watching our own stellar destiny unfold across space. Gravity works identically everywhere in the cosmos. Nuclear physics operates the same way in every star. The fundamental forces that govern stellar evolution never vary across space or time. Scientists have tested these physical laws using stars in distant galaxies billions of light years away. The same nuclear reactions occur. The same gravitational effects operate. The same evolutionary sequences unfold. This universality of physics makes stellar prediction possible. Our Sun obeys identical laws to every other star of similar mass throughout cosmic history. The rules never change. Stellar evolution follows physical law as reliably as planets orbiting the Sun. Once scientists understand the physics, they can predict stellar death with mathematical certainty. Decades of astronomical observation have confirmed theoretical predictions about stellar evolution. Scientists predicted that certain types of stars should exist. Telescopes found them exactly where theory suggested. The evidence includes planetary nebula surrounding dying stars, white dwarf remnants with predicted temperatures, red giant stars with the expected sizes. Every prediction has been verified by direct observation. Advanced space telescopes can now observe stellar evolution happening in real time. Time-lapse photography shows stars changing over periods of years and decades. The observations match theoretical predictions perfectly. This overwhelming evidence gives scientists complete confidence in stellar evolution theory. The physics has been tested and verified countless times. Our sun's future follows known and predictable paths. Stars lighter than our sun follow completely different evolutionary paths. They burn hydrogen much more slowly and live for trillions of years. Their deaths involve gradual cooling rather than dramatic expansion. Stars heavier than about 8 solar masses explode as supernovae. These massive stars burn through their fuel rapidly and end their lives in violent explosions that can outshine entire galaxies. Our sun sits precisely in the middle range, heavy enough to create complex nuclear chemistry, light enough to avoid explosive death. This mass range guarantees a specific type of stellar evolution. The mass boundary determines stellar fate with absolute precision. Stars just slightly lighter than our sun evolve differently. Stars just slightly heavier explode as supernova. Mass equals destiny in the stellar universe. Stellar evolution operates on timescales that challenge human understanding. Our sun's death process will unfold over billions of years. Each phase lasts longer than Earth's entire geological history. Human civilization has existed for less than 10,000 years. Our sun will continue burning hydrogen for another 5 billion years. The subsequent death phases will require additional billions of years to complete. This vast timescale means stellar evolution appears frozen from human perspective. The changes happen too slowly for any person to observe during a lifetime. Only modern astronomy reveals the underlying cosmic drama. Despite the enormous timescales involved, the physics operates with precise timing. Scientists can predict stellar events to within millions of years. The cosmic clockwork runs with mathematical reliability across these unimaginable time periods. Deep in our sun's center, scientists expect the first signs of fuel shortage are beginning on astronomical timescales. The core temperature remains steady at millions of degrees, but hydrogen atoms are becoming scarce after nearly 5 billion years of continuous burning. Nuclear fusion reactions depend on hydrogen density in the core. As hydrogen converts to helium, fewer hydrogen atoms remain available for fusion. Think of it like a campfire running out of wood. The flames start to weaken. Our sun's core originally contained pure hydrogen gas. Today, that same region holds a mix of hydrogen and helium. The helium acts like ash from a fire. It cannot burn at current core temperatures. This fuel dilution marks the beginning of our sun's transformation from stable star to dying giant. The nuclear engine that has powered Earth for billions of years faces its first serious energy crisis. Gravity never stops trying to crush our sun into a tiny ball. For 5 billion years, nuclear explosions have pushed back against this crushing force. When fusion weakens, gravity finally gains the upper hand. The sun's center starts contracting under its own immense weight. This compression happens slowly at first, but gravitational collapse accelerates as the process continues. The core becomes denser and hotter as it shrinks. Core compression releases gravitational energy. This energy heats the remaining hydrogen to even higher temperatures. The increased heat actually makes fusion reactions more efficient for a brief period. Gravity's victory over nuclear pressure triggers every subsequent stage of stellar death. Our sun's internal structure will never return to its current stable configuration. Something remarkable happens just outside our sun's exhausted core. A shell of fresh hydrogen surrounds the helium center. This hydrogen sits at exactly the right temperature to ignite violent nuclear burning. Shell burning operates very differently from core fusion. The shell burns hydrogen in sporadic bursts rather than steady reactions. These bursts produce more energy than our sun's core generates today. Scientists call this process hydrogen shell burning. The shell sits like a thin layer between the dead core and the outer regions. It becomes our sun's primary energy source after core hydrogen depletes. This shell burning phase makes dying stars more powerful than healthy ones. Our sun will actually brighten significantly as it approaches death. Shell fusion saves our star from immediate collapse. Our sun will become dramatically brighter during its death throes. Shell burning produces roughly 10 times more energy than current core fusion. This excess energy must escape somehow through the star's surface. The increased energy output causes our sun's total brightness to rise steadily. Astronomers call this measurement stellar luminosity. Our dying sun will eventually outshine its current brightness by an enormous factor. This brightening happens gradually over millions of years. Earth will experience slowly increasing solar energy. The extra heat will eventually make our planet uninhabitable for current life forms. Stellar brightening signals the beginning of the red giant phase. Every sun-like star follows this same luminosity increase as shell burning takes over from core fusion. Inside our current sun, energy moves outward through radiation. Photons of light bounce randomly through the dense interior. This process takes thousands of years for energy to reach the surface from the core. Shell burning creates so much energy that radiation cannot carry it all away efficiently. The star develops a new energy transport method called convection. Hot gas physically rises toward the surface while cool gas sinks inward. Convection works like boiling water in a pot. Hot bubbles rise to the top. Cool liquid sinks to the bottom. This creates circulation patterns throughout the star's interior. These convection currents will eventually reach our sun's surface. They will bring material from deep inside directly to the visible exterior. This process fundamentally changes the star's chemical composition at the surface. Our sun's surface will actually become cooler even as the star produces more total energy. This seems impossible but happens because the star's surface area increases dramatically during death. Surface temperature determines a star's color. Our current yellow sun burns at about 6,000 degrees at its surface. A dying sun's surface cools to roughly half that. This lower temperature creates red light instead of yellow. The total energy output increases even though surface temperature drops. Think of a small hot light bulb versus a large cool heater. The heater produces more total warmth despite feeling cooler to touch. This cooling surface temperature explains why dying stars appear red. Our sun will transform from yellow to red as its surface expands and cools during the death process. Our sun's current internal structure consists of distinct layers with specific functions. The core burns hydrogen. The radiation zone transports energy outward. The convection zone circulates hot gas near the surface. Shell burning completely reorganizes this layered structure. The star develops multiple burning zones at different depths. Each zone operates at different temperatures and produces different nuclear reactions. Density distribution changes throughout the interior. The center becomes much denser as it contracts. The outer regions become much less dense as they expand. These changes affect every aspect of stellar physics. Scientists call this process stellar restructuring. The dying star bears little resemblance to its former organized internal architecture. The transformation affects the entire star from center to surface. For nearly 5 billion years, our sun has maintained perfect energy balance. Nuclear energy production exactly equals energy radiated into space. This balance has never wavered significantly during our sun's main sequence lifetime. Shell burning destroys this equilibrium permanently. Energy production becomes variable and unpredictable. Sometimes the shell burns vigorously. Sometimes it nearly extinguishes before reigniting. These energy fluctuations cause our sun to pulsate like a beating heart. The star periodically expands and contracts. Its brightness varies on timescales that can stretch from short cycles to very long ones. Stellar pulsation marks the transition from stable star to chaotic dying giant. Our sun's 5 billion years of reliability end forever when shell burning begins. Shell burning produces helium atoms as a waste product of hydrogen fusion. These helium atoms accumulate in the central region, where core fusion originally occurred. The helium cannot burn at current core temperatures. Our sun's center gradually fills with helium like a cosmic recycling bin. This helium will eventually reach sufficient density and temperature to ignite its own nuclear reactions. Helium burning requires much hotter conditions than hydrogen burning. The helium accumulation process takes hundreds of millions of years. The dead core grows larger and denser as more helium collects. Eventually, this helium will become our sun's next fuel source. This helium buildup sets the stage for the next dramatic phase of stellar evolution. When helium finally ignites, it will trigger even more violent changes throughout our dying star. Our sun spent nearly 10 billion years slowly burning hydrogen in its core. This main sequence phase represents the longest period of any star's life. Nuclear fuel burns efficiently and steadily during this stable time. Shell burning accelerates stellar evolution dramatically. Changes that would normally take billions of years now occur over millions of years. The dying star races through evolutionary phases at breakneck cosmic speed. This acceleration happens because shell burning operates less efficiently than core fusion. The star burns through its remaining fuel much faster. Each subsequent evolutionary phase becomes progressively shorter. Time itself speeds up during stellar death. Our sun's remaining lifespan after leaving the main sequence equals a tiny fraction of its total lifetime. The cosmic clock runs faster as death approaches. Shell burning generates far more heat than our sun's outer layers can handle efficiently. This excess energy pushes against the star's outer atmosphere with incredible force. The pressure overwhelms the star's ability to contain itself. Our sun's outer layers will balloon outward in response to this internal heating. The expansion happens gradually over millions of years. The star's diameter will eventually grow several hundred times larger than its current size. Stellar expansion works like heating air inside a balloon. The hot gas takes up much more space than cool gas. Our sun's atmosphere will puff up to enormous proportions as shell burning pumps energy outward. This dramatic size increase transforms our ordinary sun into what astronomers call a red giant star. The expansion phase represents the most visually spectacular stage of our sun's death process. Gravity holds our sun's atmosphere in place right now. The star's immense mass creates enough gravitational force to contain all its outer layers. Surface gravity on our current sun measures about 28 times stronger than Earth's gravity. Expansion dramatically weakens this gravitational grip. As the star grows larger, its surface moves farther from the center. Gravitational force decreases rapidly with distance according to physical laws. Surface gravity will drop to just a few times Earth's gravity during maximum expansion. This represents a large decrease from current levels. The weakened gravity can barely hold onto the star's outer atmosphere. Reduced surface gravity makes mass loss inevitable during the red giant phase. Our sun's outer layers will begin escaping into space for the first time in its existence. Our sun currently shines with yellow-white light because its surface temperature reaches about 6,000 degrees Celsius. This high temperature produces the familiar golden color we see during daylight hours. Expansion spreads the same amount of energy over a much larger surface area. Think of stretching a fixed amount of butter over a bigger piece of bread. The energy density at the surface decreases significantly. Surface temperature will drop to roughly 3,000 degrees during maximum expansion. This cooler temperature produces red light instead of yellow light. The star literally changes color as it expands. Red light has longer wavelengths than yellow light. Cooler stars always appear redder than hotter stars. This color change gives red giant stars their distinctive appearance and name. Expansion and weakened gravity combine to create powerful stellar winds. These winds consist of hot gas streaming away from the star's surface at high speeds. Think of them as cosmic hurricanes blowing material into space. Our current sun loses only tiny amounts of mass through gentle solar wind. A red giant sun will lose mass at rates millions of times higher. These violent stellar winds will strip away significant portions of our star's outer layers. Scientists call this process mass loss through stellar winds. The escaping material carries away energy and helps regulate the star's internal pressure. Mass loss becomes essential for stellar survival during the red giant phase. Over several million years, stellar winds will remove roughly half of our sun's total mass. This represents an enormous amount of material being scattered throughout the solar system. Red giant stars develop a rhythmic pulsation pattern like a cosmic heartbeat. Our sun will periodically expand and contract during its red giant phase. These pulsations occur over time periods ranging from months to years. Pulsation happens because shell burning operates in an unstable manner. Sometimes the nuclear shell burns vigorously and produces excess energy. Sometimes the burning weakens and energy production drops. These energy fluctuations cause the star's outer layers to respond like a spring. Extra energy makes the star expand. Reduced energy allows gravity to compress the outer layers back inward. Variable brightness accompanies these size changes. Our sun will appear brighter during expansion phases and dimmer during contraction phases. This creates what astronomers call a pulsating variable star. Shell burning creates massive convection currents throughout our sun's interior. These currents work like giant conveyor belts carrying hot material upward and cool material downward. The circulation extends from deep inside the star all the way to its surface. Convection in stars operates on scales that dwarf any Earth phenomena. Individual circulation cells can be larger than entire planets. The hot gas moves at speeds of several kilometers per second. These convection currents will eventually reach our sun's visible surface as part of deeper mixing. Currently, our sun's surface shows convection, but it does not connect as directly to deep interior layers. Red giant convection will create visible turbulence across the entire stellar surface. Deep convection fundamentally changes how energy moves through the dying star. Instead of slowly radiating outward, energy gets physically carried upward by moving gas. Convection currents bring material from deep inside our sun directly to its surface. This material contains elements that were created by nuclear reactions in the star's interior over billions of years. Our sun's current surface consists almost entirely of hydrogen and helium. The deep interior contains heavier elements like carbon, nitrogen, and oxygen created by nuclear fusion. Normally, these elements remain buried far below the surface. Convection mixing will bring these heavy elements to our sun's surface for the first time. Astronomers call this process dredge up. The surface composition changes dramatically as buried material rises upward. This chemical change will be detectable from Earth using specialized telescopes. Scientists will be able to observe elements in our Sun's atmosphere that were previously hidden in its deep interior. Our expanding Sun will eventually grow large enough to engulf the closest planets in our solar system. The red giant phase will extend our star's surface beyond Mercury's orbit and possibly beyond Venus's orbit. Mercury orbits about 58 million kilometers from our Sun's current surface. During maximum expansion, our Sun's surface will extend roughly 100 million kilometers outward. This places Mercury well inside the expanded star's atmosphere. Venus orbits at 108 million kilometers and sits right at the boundary of our Sun's maximum expansion. Whether Venus gets swallowed depends on exactly how large our Sun grows during its red giant phase. Any planet caught inside our expanded Sun's atmosphere will spiral inward and eventually be destroyed. The planets will not survive passage through the hot, dense stellar material. Planets caught within our Sun's expanded atmosphere will experience powerful atmospheric drag. The stellar material acts like thick cosmic soup that resists planetary motion. This creates friction that slowly robs planets of their orbital energy. Atmospheric drag works like trying to swim through honey instead of water. The planets encounter increasing resistance as they orbit through the dense stellar material. Their orbital speed gradually decreases over time. Decreasing orbital speed causes the planets to spiral inward toward our Sun's center. Each orbit brings them closer to the stellar core, where temperatures and densities become lethal. The process accelerates as they fall deeper into the star. This orbital decay process is called tidal friction. Mercury and possibly Venus will experience this fate during our Sun's red giant expansion. Shell burning not only makes our Sun larger but also dramatically more luminous. Our dying star will eventually produce thousands of times more energy than it does today. This represents one of the most extreme brightness increases possible. Total energy output depends on both surface temperature and surface area. Even though the surface becomes cooler, the enormous increase in surface area more than compensates for the temperature drop. Our red giant Sun will shine with the brightness of thousands of current suns combined. This intense energy output will be visible across interstellar distances. Other civilizations could easily detect our dying star from light years away. Extreme brightness makes red giant stars among the most luminous objects in the galaxy. Our modest Sun will temporarily join the ranks of cosmic lighthouses during its death throes. Our Sun's dramatic brightness increase will create lethal conditions throughout the inner solar system. Earth will receive thousands of times more energy than it does today. This excess heat will destroy our planet's ability to support life. Earth's oceans will boil away completely within a relatively short time period. The increased solar energy will heat our planet's surface to temperatures exceeding 1,000 degrees Celsius. No liquid water can survive under these extreme conditions. Our planet's atmosphere will be stripped away by the intense solar radiation and stellar winds. The same forces that remove mass from our dying Sun will also remove Earth's protective atmospheric blanket. Earth will transform from a blue ocean world into a scorched, airless rock during our Sun's red giant phase. The planet may survive as a solid object, but it will become completely uninhabitable. Astronomers use a special diagram called the Hertzsprung-Russell diagram to track stellar evolution. This chart plots star brightness against surface temperature. Different types of stars occupy different regions on this diagram. Our Sun currently sits in the middle area of this diagram where normal, stable stars spend most of their lives. This region is called the main sequence. Our Sun has remained in this location for nearly 5 billion years. During the red giant phase, our Sun will move to the upper right portion of the diagram. This region contains large, cool, very bright stars. The movement traces our Sun's transformation from ordinary star to giant. Stellar evolution paths on this diagram are predictable and well understood. Thousands of similar stars have been observed making this same journey from main sequence to red giant status. Billions of years of hydrogen burning have left behind a massive accumulation of helium in our Sun's center. This helium acts like nuclear waste that cannot burn at current core temperatures. The helium just sits there, collecting in ever larger amounts. Core temperature begins rising dramatically as gravitational compression intensifies. The helium requires much hotter conditions to ignite than hydrogen ever did. Scientists call this temperature threshold about 100 million degrees Celsius. As compression continues, our Sun's core approaches this critical helium ignition temperature. The accumulated helium transforms from inert waste into potential nuclear fuel. Decades of gradual heating bring the core closer to an explosive tipping point. This temperature rise creates the most dangerous period in our Sun's entire existence. The massive helium stockpile will eventually detonate in a cosmic explosion that dwarfs anything our star has previously experienced. Helium burning requires a much more complex nuclear reaction than hydrogen burning. Scientists call this process the triple alpha reaction. 3 helium nuclei must collide simultaneously to create a carbon nucleus. Alpha particles are the scientific name for helium nuclei. Each helium nucleus contains 2 protons and 2 neutrons bound together. The triple collision happens when 3 of these particles smash together at incredibly high speeds. This triple collision occurs only at extreme temperatures and pressures. The probability remains extremely low even under ideal conditions. Billions of attempted collisions happen before one succeeds in creating carbon. Once carbon nuclei form, they can capture additional helium nuclei to create oxygen. This nuclear assembly line produces the heavy elements that will eventually become part of planets and living organisms. Our Sun's core enters an exotic state of matter called electron degeneracy as compression intensifies. Normal matter consists of atoms with electrons orbiting around nuclei. Degenerate matter crushes these atoms until electrons cannot maintain their normal orbital patterns. Electron degeneracy creates material with density comparable to white dwarf stars. A teaspoon of this degenerate matter would weigh several tons on Earth. The electrons become packed together far more tightly than normal atomic structure allows. This crushed state follows different physical laws than normal matter. Quantum mechanics governs the behavior of degenerate matter rather than classical physics. The material becomes almost incompressible despite the enormous pressures involved. Our Sun's core temporarily transforms into a white dwarf-like object while still buried inside a normal star. This bizarre hybrid structure creates the conditions necessary for explosive helium ignition. Normal matter expands when heated and contracts when cooled. This thermal expansion provides a safety valve that prevents runaway nuclear reactions. Hot gas automatically expands and reduces its own density and reaction rate. Degenerate matter behaves completely differently from normal matter when heated. Temperature increases do not cause expansion in degenerate material. The density remains constant regardless of how hot the material becomes. This temperature independence eliminates the natural safety mechanisms that regulate nuclear burning in normal stars. Heating degenerate matter does not reduce its density or slow down nuclear reactions. Degenerate matter's strange properties set the stage for catastrophic runaway nuclear burning. Without thermal expansion to provide automatic regulation, helium fusion can accelerate without any natural limits. Runaway nuclear reactions occur when fusion heating fails to regulate itself through normal expansion. In our Sun's degenerate core, increased fusion creates more heat without reducing reaction rates. More heat triggers even faster fusion in an accelerating spiral. Nuclear physicists call this process thermal runaway. Each fusion event releases energy that heats nearby material. Hotter material undergoes fusion more rapidly. Faster fusion releases more energy and heats the material even further. Normal stars avoid thermal runaway because hot gas expands and becomes less dense. Lower density reduces fusion rates and automatically controls the reaction. Our Sun's degenerate core cannot expand to regulate itself. This runaway process continues accelerating until the entire degenerate core ignites nearly simultaneously. The lack of self-regulation turns controlled fusion into explosive detonation across the entire stellar center. The helium flash occurs over a time period of just a few hours. Nearly 5 billion years of gradual stellar evolution culminate in this brief explosive event. The entire core detonates in what amounts to cosmic nanoseconds. During these crucial hours, our Sun's core releases more energy than it has produced during millions of previous years. The explosion happens too rapidly for the energy to escape through the star's outer layers immediately. Core temperature spikes to over 1 billion degrees during the flash. This represents the hottest our Sun's interior will ever become. The extreme conditions create nuclear reactions that are impossible under normal stellar conditions. Most of this explosive energy gets absorbed by the surrounding stellar material rather than escaping into space. The flash occurs so deep inside our Sun that its effects take a long time to reach the surface. Extreme heating during the helium flash breaks the electron degeneracy that has trapped our Sun's core. The enormous energy release forces the crushed matter to expand back into normal gas. Scientists call this process degeneracy lifting. Expansion happens almost instantaneously once the degeneracy breaks. The core material transforms from supercompressed solid-like matter back into normal stellar gas within hours. This represents one of the most rapid phase transitions possible in nature. Normal gas behavior returns to our Sun's core for the first time in millions of years. The restored thermal expansion provides automatic regulation that prevents further runaway reactions. Nuclear fusion rates stabilize at sustainable levels. This return to normal matter ends the explosive phase and begins a new period of stable helium burning. Our Sun's core resumes controlled nuclear reactions under normal stellar physics. The enormous energy required to expand degenerate matter absorbs most of the helium flash's explosive power. Expansion works like a cosmic shock absorber that soaks up energy that would otherwise destroy our Sun. Degeneracy lifting requires tremendous amounts of energy to break the quantum mechanical forces holding the compressed matter together. This energy comes directly from the explosive helium fusion reactions. By the time the core finishes expanding back to normal gas, most of the flash energy has been consumed. The remaining energy settles into normal stellar heating rather than continuing explosive reactions. This energy absorption mechanism saves our Sun from complete destruction during the helium flash. without expansion to absorb the explosion. The flash would tear our star apart rather than simply rearranging its internal structure. The helium flash's effects take considerable time to propagate from our sun's center to its visible surface. Energy must travel through thousands of kilometers of stellar material before reaching the outside layers, where we can observe changes. Heat transport through stellar material happens much more slowly than the flash itself. Energy moves outward through radiation and convection over long timescales rather than hours. Our sun's surface will show only subtle changes following the helium flash. Slight brightness variations and minor temperature fluctuations may occur, but nothing approaching the violence of the internal explosion. External observations would miss the most dramatic event in our sun's post-main sequence evolution. The helium flash represents invisible internal restructuring rather than obvious external transformation. Following the helium flash, our sun establishes a new stable configuration with helium burning peacefully in its core. Astronomers call this evolutionary phase the horizontal branch because of its position on stellar evolution diagrams. Helium fusion produces carbon and oxygen, nuclei as its primary products. These heavier elements accumulate in the core while helium burning continues in a controlled manner. The star operates two different nuclear furnaces simultaneously. Core helium burning provides steady energy production for several million years. This represents our sun's second period of relative stability after the main sequence phase. Nuclear reactions proceed at sustainable rates without explosive tendencies. This horizontal branch phase demonstrates our sun's remarkable ability to recover from near destruction and establish new equilibrium conditions. Stellar evolution continues despite surviving the most violent internal explosion possible. Our sun develops two separate nuclear burning regions after the helium flash settles. The inner core burns helium into carbon and oxygen. A surrounding shell continues burning hydrogen into helium. This dual fuel system creates what astronomers call double shell burning. Each nuclear zone operates independently with different fuel sources, reaction rates, and energy outputs. The star becomes far more complex than during its simple main sequence phase. The hydrogen shell provides most of the energy that reaches our sun's surface. The helium core burns more slowly but creates the heavy elements that will eventually become part of planetary systems and biological molecules. Double shell burning marks the beginning of our sun's final approach toward complete nuclear exhaustion. Both fuel sources will eventually deplete, leading to the ultimate stellar death sequence that no nuclear reactions can prevent. After the helium flash settles, our sun enters its most chaotic evolutionary phase. Astronomers call this stage the asymptotic giant branch, or AGB for short. The name describes how stars move on stellar evolution charts during this period. AGB stars operate like poorly designed nuclear reactors with multiple unstable fuel sources. Our sun will burn helium in its core while simultaneously burning hydrogen in a shell above it. This dual burning system creates inherently unstable conditions. The star's internal structure becomes extremely top-heavy during this phase. Most of the star's mass concentrates in a tiny central core, while enormous outer layers extend far into space. This creates gravitational instability throughout the entire structure. Our sun's AGB phase represents the most structurally unstable period in its entire existence. The star struggles to maintain basic equilibrium while operating multiple nuclear furnaces simultaneously. Helium shell burning operates in violent bursts rather than steady reactions. These nuclear outbursts occur roughly every 100,000 years during our Sun's AGB phase. Scientists call these events thermal pulses because they send waves of energy throughout the star. Each thermal pulse begins when helium accumulates to critical levels in the burning shell. The helium suddenly ignites in a mini explosion similar to the original helium flash. The explosion sends shock waves through our Sun's outer layers. These nuclear hiccups cause our entire Sun to pulsate like a beating heart. The star expands during each pulse and then contracts before the next explosion occurs. The pulsations become visible as brightness changes that astronomers can observe from Earth. Thermal pulsation transforms our Sun from a stable energy source into an unpredictable variable star. The nuclear hiccuping will continue for several million years until the fuel finally runs out. Thermal pulses create powerful convection currents that reach from our Sun's core all the way to its surface. These currents work like cosmic elevators, bringing buried material upward for the first time in billions of years. Astronomers call this upward transport process dredge up. Each thermal pulse drives convection deeper into our Sun's interior than normal circulation can reach. The convection dredges up material that has been processed by nuclear reactions. This excavation process brings carbon, nitrogen, and oxygen from the deep interior to our Sun's visible surface. These elements were created by helium burning, but remained hidden below the surface until convection carries them upward. Dredge up fundamentally changes our surface chemistry during each thermal pulse. The star's outer layers will show clear evidence of the nuclear cooking that has occurred in its deep interior. Repeated dredge-up episodes gradually transform our Sun's surface composition from mostly hydrogen and helium to significant amounts of carbon. Helium burning produces carbon as its primary waste product, and thermal pulses bring this carbon to the surface. Carbon accumulation eventually changes our Sun's basic classification from a normal star to what astronomers call a carbon star. These stars show distinctive colors and spectral signatures that indicate carbon-rich atmospheres. Our Sun's surface temperature drops during the AGB phase, allowing carbon to form solid particles rather than remaining as gas. These carbon particles create clouds of soot, like material in our Sun's outer atmosphere. Carbon enrichment marks our Sun's transition from hydrogen-powered star to carbon-producing factory. The accumulated carbon will eventually be ejected into space, where it can form new planetary systems and potentially contribute to biological molecules. Thermal pulsations create powerful shock waves that propagate outward through our Sun's extended atmosphere. These shock waves work like cosmic sonic booms that compress and heat the stellar material as they travel outward. The shock waves accelerate stellar winds to much higher speeds than normal red giant mass loss. Our Sun will lose mass at rates thousands of times higher than during its earlier red giant phase. The accelerated winds strip away our star's outer layers. Each thermal pulse drives a new wave of mass ejection from our Sun's surface. The pulsating shock waves overcome the star's gravitational grip on its outer atmosphere. Material gets blasted away into space at high velocities. This pulsation-driven mass loss represents the primary mechanism that will eventually strip away most of our Sun's outer layers. The thermal pulse shock waves gradually dismantle our star from the outside inward. Material ejected during thermal pulses initially consists of extremely hot gas traveling at high speeds away from our Sun. As this gas moves farther from the star's heat source, it cools dramatically and undergoes a remarkable transformation. Cooling allows carbon atoms in the ejected gas to bond together and form solid particles. These particles resemble cosmic soot or fine dust grains. The transformation from hot gas to solid particles occurs over distances of several stellar radii. Dust grain formation creates visible clouds around our dying sun. These dust clouds absorb starlight and re-emit it as infrared radiation. The dust makes our sun appear dimmer in visible light, but brighter in infrared observations. Dust formation around AGB stars creates some of the primary building materials for future planetary systems. The carbon-rich particles will eventually be incorporated into asteroids, planets, and potentially life forms. Dust grains in our sun's atmosphere interact strongly with the star's intense radiation. Starlight pushes against these particles through a process called radiation pressure. Think of light as a cosmic wind that can physically move small objects. Radiation pressure affects dust particles more strongly than it affects gas atoms. The dust grains absorb photons from our sun and gain momentum from each interaction. This momentum transfer accelerates the particles away from the star. The accelerated dust particles drag surrounding gas along through gravitational and magnetic interactions. This creates a radiatively driven wind that can achieve much higher speeds than thermal winds alone. Radiation pressure on dust grains becomes the dominant mass loss mechanism during our sun's final AGB phases. The starlight literally blows away our star's outer atmosphere, using the dust as cosmic sails. Our sun will lose enormous amounts of mass during its AGB phase through the combined effects of thermal pulsations and dust-driven winds. The total mass loss will amount to roughly half of our star's current mass ejected into space. This represents one of the most dramatic weight loss programs possible for any cosmic object. Our sun will literally blow away several Earth masses worth of material every million years during the most active periods. Mass ejection rates vary dramatically depending on thermal pulse timing and dust production efficiency. During peak mass loss episodes, our sun will lose material faster than some stars gain mass through accretion. The massive weight loss fundamentally changes our sun's internal structure and future evolution. Removing the outer layers exposes deeper regions that were previously buried beneath kilometers of stellar material. AGB thermal pulsations cause our sun's brightness to vary by factors of 10 or more over periods ranging from months to years. These brightness changes make our sun what astronomers classify as a variable star. The variability occurs because thermal pulses change our sun's internal energy generation and surface area simultaneously. Increased nuclear burning makes the star brighter, while atmospheric expansion can make it dimmer. Different wavelengths of light vary by different amounts during each pulsation cycle. Our sun will appear much redder during expansion phases and less red during contraction phases. The color changes accompany the brightness variations. Variable star behavior makes our dying sun easily detectable from enormous distances across the galaxy. Other civilizations could monitor our star's death throes by observing its characteristic pulsation patterns. Our sun's AGB phase continues until thermal pulsations and mass loss finally strip away all the material capable of sustaining nuclear burning. This process removes the hydrogen and helium layers that fuel the star's energy production. Each thermal pulse removes progressively more material from our sun's outer layers. Eventually, the pulsations will excavate down to regions where no more nuclear fuel exists. The star runs out of both fuel and the material needed to transport that fuel. Mass loss acceleration during the final thermal pulses creates a runaway process that quickly strips away the remaining stellar atmosphere. Our Sun transitions from massive giant star to exposed stellar core within a relatively short time period. The end of the AGB phase occurs when our Sun can no longer sustain the thermal pulsations that drive mass loss. Without pulsations to power the stellar winds, the remaining atmospheric material falls back toward the stellar core or gets ejected in one final burst. Mass loss during the AGB phase eventually removes so much material that our Sun's hot interior becomes directly visible for the first time. The dying star sheds its outer atmospheric layers like removing layers of clothing. What emerges underneath looks completely different from the star we know today. The exposed central core burns at temperatures exceeding 50,000 degrees Celsius. This makes it far hotter than our Sun's current surface. The naked stellar core shines with intense blue-white light instead of the familiar yellow glow. This central remnant represents what astronomers call a planetary nebula central star. The name refers to the hot stellar core that powers the spectacular light show around it. The exposed core becomes the engine that illuminates our Sun's ejected remains. Our Sun's transformation from cool red giant to blazing central star marks the beginning of one of astronomy's most beautiful phenomena. The hot core provides the energy source needed to create glowing cosmic artwork from previously invisible stellar material. The intensely hot central star produces vast amounts of ultraviolet radiation that cannot be seen by human eyes. This invisible radiation travels outward and encounters the gas clouds that our Sun ejected during its AGB phase. The interaction creates one of nature's most spectacular light shows. Ultraviolet photons carry enough energy to strip electrons away from atoms in the surrounding gas clouds. Scientists call this process ionization. When atoms lose their electrons, they become electrically charged particles called ions. Ionized gas behaves very differently from normal gas. The separated electrons eventually recombine with the charged ions, releasing visible light in the process. Different elements produce different colors when their electrons recombine. This ionization and recombination process transforms our Sun's invisible ejected material into brilliantly glowing gas clouds. The previously dark stellar debris becomes illuminated like a cosmic neon sign powered by the central star's ultraviolet radiation. Gas ejected during our Sun's final mass loss episodes expands outward in roughly spherical shells. These expanding gas bubbles travel through space at speeds of several tens of kilometers per second. The expansion continues for thousands of years after the initial ejection. Multiple ejection episodes during different thermal pulses create nested shells of material expanding at different speeds. Earlier ejections travel farther from the central star, while later ejections remain closer. This creates a complex layered structure. The expanding shells maintain their basic shape as they travel through space. Gravity from the central star is too weak to significantly affect the motion of the ejected material. The shells preserve a record of our Sun's final death throes. Expansion creates the characteristic bubble-like appearance that gives planetary nebulae their distinctive shapes. The spherical geometry reflects the roughly symmetric mass loss that occurs during the final stages of stellar evolution. Our Sun's transition from AGB giant to planetary nebula central star creates two very different types of stellar winds. The slow AGB winds moved at modest speeds while ejecting large amounts of material. The fast central star winds achieve much higher velocities but carry less mass. The fast winds cannot pass through the slow-moving material ahead of them. Instead, the high-speed winds pile up against the dense, slow-moving shells. This collision creates shock wave structures throughout the expanding nebula. Scientists call these collision zones interacting stellar winds. The shock waves heat gas to extreme temperatures and create complex flow patterns throughout the planetary nebula. The interactions sculpt the nebula's internal structure. These shock wave boundaries become visible as bright rims and filaments within the glowing gas clouds. The stellar wind interactions create much of the fine detail that makes planetary nebula so visually striking and scientifically interesting. Different chemical elements emit light at very specific wavelengths when their electrons recombine after ionization. This process works like atomic fingerprinting. Each element produces its own unique set of colors that astronomers can identify using special instruments. Hydrogen atoms emit red light when their electrons recombine. Oxygen atoms produce green and blue-green light. Nitrogen creates red and blue colors. The mix of elements determines the overall color scheme of each planetary nebula. Scientists call this light emission process fluorescence. The atoms absorb high-energy ultraviolet photons from the central star and re-emit the energy as lower-energy visible light photons. This energy conversion makes the invisible ultraviolet radiation visible to our eyes. Fluorescence efficiency depends on gas temperature and density throughout the nebula. Different regions emit different colors based on their physical conditions. This creates the complex color patterns that make each planetary nebula unique and beautiful. Our Sun's magnetic field and rotation combine with stellar winds to create asymmetric structures during planetary nebula formation. Perfect spheres rarely occur in real nebulae. Instead, most show complex shapes including rings, jets, and bipolar lobes. Magnetic fields can channel stellar winds into narrow streams that create jet-like features extending far from the central star. Stellar rotation causes these jets to precess like cosmic garden sprinklers, creating intricate patterns in the surrounding gas. Binary star companions also influence nebula shapes when present. Gravitational interactions with companion stars can create spiral patterns and asymmetric mass loss during the AGB phase. These effects become visible in the final nebula structure. The complex shapes reflect the detailed physics of stellar death rather than simple spherical expansion. Each planetary nebula preserves a record of the magnetic field's rotation and possible companions that influenced our Sun's final evolution. Temperature variations throughout a planetary nebula create distinctive color zones that astronomers can observe and measure. Gas closest to the central star experiences the most intense radiation and reaches the highest temperatures. Cooler regions exist farther from the central energy source. Hot inner regions emit blue and green light from highly ionized oxygen and other heavy elements. Intermediate zones produce red light from hydrogen recombination. Cool outer edges may show red light from nitrogen and other elements that ionize at lower energies. The temperature structure creates concentric color shells that change over time as the central star evolves. Initially hot central stars gradually cool down, which changes the ionization patterns and color distribution throughout the nebula. These temperature-dependent color variations make planetary nebula some of the most photogenic objects in space. The natural color gradients create artistic compositions that rival any human-created artwork. Planetary nebula expansion occurs over timescales much longer than human lifetimes, but much shorter than most other astronomical processes. The visible nebula phase lasts roughly 10,000 years from initial formation until it becomes too faint to observe easily. Gas shells expand at speeds that allow astronomers to measure their growth directly using telescopes. Advanced imaging techniques can detect size changes over periods of just a few years. This makes planetary nebulae among the few astronomical phenomena where motion is directly observable. The expansion rate depends on the initial ejection velocity and the resistance provided by surrounding interstellar material. Nebulae expanding into dense regions slow down more quickly than those expanding into empty space. Time-lapse observations reveal how planetary nebulae evolve from compact, bright objects into large, faint structures. The gradual expansion provides astronomers with real-time movies of stellar death unfolding across cosmic timescales. Planetary nebula formation distributes heavy elements created during our Sun's lifetime throughout the surrounding interstellar space. Carbon, nitrogen, and oxygen produced by nuclear burning become available for incorporation into future generations of stars and planets. These heavy elements are essential building blocks for rocky planets and biological molecules. Our dying sun will contribute carbon that could eventually become part of diamond crystals, organic compounds, or even DNA molecules in distant future life forms. The ejected material mixes with existing interstellar gas and becomes part of the cosmic recycling system. Elements forged in our sun's nuclear furnace will outlive the star itself and participate in new cycles of star formation and planetary development. Our sun's death enriches the galaxy's chemical composition and contributes to the cosmic evolution that makes complex chemistry and biology possible. Stellar death becomes an act of cosmic generosity rather than mere destruction. Planetary nebulae gradually fade as their central stars cool down and produce less ionizing radiation. Without sufficient ultraviolet energy to maintain ionization, the gas stops glowing and becomes invisible against the dark background of space. The central star evolves into a white dwarf that cools steadily over billions of years. As the star's surface temperature drops, it produces fewer high-energy photons. The reduction in ionizing radiation causes the nebula to fade progressively. Additionally, the expanding gas shells become increasingly dilute as they spread through larger volumes of space. Lower gas density reduces the efficiency of light emission even when ionizing radiation remains available. Most planetary nebulae become undetectable within 50,000 years of formation. The beautiful cosmic artwork represents a brief but spectacular finale to billions of years of stellar evolution before fading into cosmic obscurity. Material ejected during planetary nebula formation eventually disperses throughout the galaxy and becomes available for future star and planet formation. This cosmic recycling ensures that heavy elements created during stellar evolution get distributed widely through space. The expanding nebula shells sweep up additional interstellar material as they travel through space. This process creates shock waves that can trigger new episodes of star formation in nearby gas clouds. Our dying sun helps create conditions for new stellar births. Planetary nebula material contributes to the gradual chemical enrichment of the galaxy over cosmic time. Each generation of dying stars adds more heavy elements to the mix available for subsequent star and planet formation. This recycling process connects our sun's death to the future formation of new planetary systems that could potentially harbor life. The elements dispersed by our dying star will participate in cosmic evolution long after our solar system has ceased to exist. After ejecting its outer layers as a planetary nebula, our sun's remaining core faces the ultimate cosmic squeeze. Nuclear fusion has completely stopped throughout the entire stellar remnant. No more energy generation occurs anywhere within the collapsed core. Without nuclear pressure to resist gravitational collapse, our sun's core contracts to the smallest possible size that physics allows. The compression continues until quantum mechanical forces finally halt the shrinking process. Scientists call this incredibly dense final state a white dwarf star. The core that once occupied a region hundreds of thousands of kilometers across now fits within a sphere roughly the size of Earth. This extreme compression represents the maximum density that normal matter can achieve before exotic physics takes over. Our sun's core becomes crushed to the absolute limit of what electrons and atomic nuclei can withstand. Quantum mechanics provides the only force capable of stopping our sun's final gravitational collapse. A principle called the Pauli exclusion principle prevents electrons from occupying the same quantum state simultaneously. This creates what physicists call electron degeneracy pressure. Electron degeneracy pressure works completely differently from normal gas pressure. Regular gas pressure depends on temperature and particle motion. Degeneracy pressure depends only on density and operates even at absolute zero temperature. The crushed electrons in our white dwarf core resist further compression through pure quantum mechanical effects. No amount of gravitational force can squeeze the electrons closer together once they reach their quantum mechanical limit. This quantum foundation provides permanent structural support that will last longer than the current age of the universe. Electron degeneracy pressure makes white dwarf stars among the most stable objects in the cosmos. Our white dwarf sun will achieve densities that challenge human comprehension. A sugar cube-sized piece of white dwarf material would weigh roughly the same as an automobile on Earth. The entire mass of our current sun gets compressed into a volume smaller than Earth. This extreme density results from removing all the empty space that normally exists within atoms. In ordinary matter, atomic nuclei occupy tiny fractions of atomic volume, while electrons orbit in mostly empty space. White dwarf compression eliminates this emptiness. The nuclei and electrons get packed together as tightly as quantum mechanics allows. Matter approaches the density found inside atomic nuclei themselves. Only neutron stars achieve higher densities than white dwarf material. White dwarf density represents one of the most extreme states of matter possible in the universe. Our dying sun's core becomes compressed beyond anything achievable in earthly laboratories. Our newly formed white dwarf will shine with surface temperatures exceeding 100,000 degrees Celsius. This makes it far hotter than our current sun's surface temperature. The dead stellar core initially glows with brilliant blue-white light. Extreme surface temperature results from the enormous gravitational energy released during core collapse. Compression heats the white dwarf material to temperatures much higher than nuclear fusion ever achieved in our living sun. The intense heat gets trapped within the white dwarf's incredibly dense material. Heat conduction occurs very slowly through the compressed matter. This thermal insulation keeps the surface hot for extremely long periods. Despite being much smaller than our current sun, the white dwarf initially produces comparable amounts of light due to its extreme surface temperature. Death paradoxically makes our sun burn brighter than life ever did. Our white dwarf sun contains no internal energy source to maintain its high temperature. The heat comes entirely from leftover thermal energy trapped during the collapse process. This stored heat slowly leaks away through radiation from the surface. Cooling proceeds extremely gradually due to the white dwarf's incredible thermal mass and poor heat conduction. The dense material acts like a cosmic thermos bottle that retains heat for astronomical time periods. Scientists calculate that white dwarf cooling requires trillions of years to reach low temperatures. Our sun will continue glowing for periods longer than the current age of the universe before becoming truly cold. The cooling process transforms our white dwarf from brilliant blue-white to yellow to red to infrared over cosmic timescales. Eventually, it will become too dim to observe with normal telescopes. Unlike every previous phase of our sun's evolution, the white dwarf phase involves no nuclear reactions whatsoever. The stellar remnant becomes a purely cooling object that radiates away its stored thermal energy without generating any new heat. Nuclear fusion becomes impossible in white dwarf material due to the extreme electron degeneracy conditions. The quantum mechanical environment prevents the nuclear reactions that powered our sun for billions of years. Our white dwarf sun transforms from an active energy producer into a passive energy radiator. It joins the cosmic graveyard of stellar remnants that slowly fade over trillion-year timescales. This marks the definitive end of our sun's career as a functioning star. The white dwarf phase represents stellar retirement rather than active stellar life. Surface gravity on our white dwarf sun will exceed Earth's gravity by factors of hundreds of thousands. Anything placed on the white dwarf surface would be instantly crushed into a pancake-thin layer. This extreme gravity results from concentrating our sun's entire mass within Earth's volume. Gravitational force depends on mass divided by the square of radius. Shrinking our sun to Earth size while maintaining its mass creates crushing gravitational fields. The intense gravity affects light itself through gravitational redshift. Photons climbing out of the white dwarf's gravitational well lose energy and shift toward redder wavelengths. This effect becomes easily measurable from Earth. Extreme surface gravity makes white dwarf stars natural laboratories for testing Einstein's theory of general relativity under conditions impossible to recreate on Earth. The white dwarf's extreme gravity creates perfect conditions for atmospheric stratification. Heavy elements sink toward the surface while light elements float upward. This process separates different atomic species into distinct layers. Hydrogen, being the lightest element, rises to form the outermost atmospheric layer. Helium settles beneath the hydrogen. Heavier elements like carbon and oxygen concentrate near the solid surface. This gravitational sorting happens rapidly compared to white dwarf cooling timescales. Within thousands of years, the atmosphere develops a layered structure with composition varying by depth. Atmospheric stratification makes white dwarf surfaces appear almost pure hydrogen when observed from Earth. The heavier elements remain hidden beneath the light element layers. As our white dwarf cools over billions of years, the carbon and oxygen nuclei in its interior begin forming crystalline structures. The nuclei arrange themselves into organized lattices similar to crystal formation in minerals. Crystallization in white dwarf interiors creates structures similar to diamond crystals on Earth. Carbon nuclei arrange themselves in the same geometric patterns found in terrestrial diamonds. The white dwarf core literally becomes a cosmic gemstone. This crystallization process releases additional energy that slightly slows the white dwarf's cooling rate. The phase transition from liquid to solid nuclear material provides a temporary heat source. Our cooling white dwarf sun will eventually become a massive crystalline object composed primarily of diamond-like carbon and oxygen crystals. The stellar remnant transforms into the largest gemstone in the solar system. White dwarf stability depends critically on the stellar remnant's total mass. A maximum mass limit called the Chandrasekhar limit determines whether a white dwarf can exist stably. Stars that exceed this limit cannot become white dwarfs. The Chandrasekhar limit equals roughly 1.4 times our current Sun's mass. Our Sun's white dwarf remnant will weigh considerably less than this limit, ensuring stable white dwarf formation. More massive stellar cores cannot be supported by electron degeneracy pressure alone. These objects collapse further and become neutron stars or black holes instead of white dwarfs. Our Sun's intermediate mass guarantees it will achieve stable white dwarf status rather than undergoing more exotic stellar death scenarios. The mass limit ensures our Sun's peaceful rather than violent final evolution. White dwarfs in binary star systems can experience dramatic revivals if material from companion stars falls onto their surfaces. This process, called accretion, can push white dwarfs beyond their stability limits. Accreted hydrogen from companion stars builds up on the white dwarf surface until conditions become right for explosive nuclear burning. These explosions, called novae, can temporarily brighten white dwarfs by factors of millions. If enough material accumulates to push the white dwarf mass beyond the Chandrasekhar limit, the entire object explodes as a Type 1a supernova. These explosions completely destroy the white dwarf and can be seen across cosmic distances. Our Sun's white dwarf will avoid these explosive fates only if it remains isolated from other stars. Binary companions transform peaceful white dwarf retirement into potentially catastrophic stellar resurrection. Our white dwarf sun will eventually cool completely and become what astronomers call a black dwarf. This represents the absolute final state of stellar evolution for stars like our Sun. Black dwarf formation requires cooling times that exceed the current age of the universe by factors of thousands. Our Sun will continue glowing as a white dwarf long after all other cosmic processes have ended. The transition from white dwarf to black dwarf marks the true death of our Sun. The black dwarf will persist as a cold, dark stellar remnant for potentially infinite time periods. Our Sun's black dwarf remnant will serve as a permanent monument to our star's existence, outlasting galaxies, black holes, and possibly the universe itself. Stellar death achieves a form of cosmic immortality. Mercury orbits dangerously close to our Sun at a distance of roughly 58 million kilometers. During the red giant expansion phase, our Sun's surface will extend outward beyond this orbital distance. Mercury will find itself flying through the hot, dense atmosphere of our expanded dying star. Venus orbits at 108 million kilometers from our current Sun. This places Venus right at the edge of our Sun's maximum red giant expansion. Whether Venus survives depends on exactly how large our Sun grows during its most extreme bloated phase. Any planet caught inside our expanded Sun's atmosphere experiences powerful atmospheric drag. The stellar material acts like thick cosmic soup that resists planetary motion. This resistance gradually robs planets of their orbital energy. Atmospheric drag causes the trapped planets to spiral inward toward our Sun's center like objects falling through honey. Mercury and possibly Venus will spiral to their complete destruction during our Sun's red giant transformation. Earth's atmosphere currently shields our planet from the harsh environment of space. This protective layer consists of nitrogen, oxygen, and other gases held in place by Earth's gravity. The atmosphere makes liquid water possible and protects life from deadly radiation. Our Sun's red giant brightness will increase by thousands of times compared to current levels. This intense energy bombardment will heat Earth's atmosphere to extreme temperatures. The heated gases will move faster and eventually escape Earth's gravitational pull. Scientists call this process atmospheric escape. The energized gas molecules achieve speeds greater than Earth's escape velocity. Once atmospheric particles reach these speeds, they fly away into space, never to return. Atmospheric stripping will remove Earth's protective blanket completely during our Sun's red giant phase. Our planet will transform from a world with breathable air to an airless rock exposed directly to space. Mars currently sits too far from our Sun to maintain liquid water on its surface. The planet's average temperature stays well below freezing throughout most of its year. Any water that exists on Mars remains locked up as ice in polar caps and underground deposits. Our Sun's dramatic brightness increase will flood the outer solar system with unprecedented amounts of energy. Mars will receive thousands of times more heat than it gets from our current Sun. This energy input will raise Martian temperatures dramatically. For a brief period, in cosmic terms, Mars may enter what scientists call the habitable zone. This represents the orbital distance where planets can maintain liquid water on their surfaces. Mars could experience a temporary spring after billions of years of frozen winter. However, this Martian warming phase will be short-lived compared to geological timescales. Our Sun's red giant phase lasts only a few million years before transitioning to other death stages that will freeze Mars once again. Our Sun will lose roughly half its total mass during the red giant and planetary nebula phases. Stellar winds and mass ejection carry enormous amounts of solar material into space. This mass loss fundamentally changes the gravitational environment throughout the solar system. Planetary orbits depend on the gravitational pull between planets and our Sun. When our Sun becomes less massive, its gravitational pull on distant planets weakens significantly. Weaker gravity cannot hold planets in their current tight orbits. The outer planets will respond to reduced solar gravity by moving to larger orbital distances. Jupiter, Saturn, Uranus, and Neptune will all drift outward as our Sun's gravitational grip loosens during its death throes. This orbital expansion saves the outer planets from the extreme heating that destroys inner worlds. Their increased distance from our dying Sun provides protection from the most lethal effects of stellar death. The asteroid belt contains millions of rocky objects orbiting between Mars and Jupiter. These asteroids currently follow stable, predictable paths around our Sun. Most asteroids complete their orbits without significant perturbations over millions of years. Our Sun's intense red giant stellar winds will create powerful forces throughout the inner solar system. These winds carry charged particles that interact with asteroid surfaces and can slightly alter their orbital motions. Small gravitational effects accumulate over time. Additionally, our Sun's mass loss changes the overall gravitational environment that keeps asteroid orbits stable. The reduced solar mass allows planetary gravitational influences to have stronger effects on asteroid trajectories. Many asteroids will experience orbital disruption during our Sun's death sequence. Some may be ejected from the solar system entirely, while others crash into planets or fall into our dying Sun. The Kuiper belt extends far beyond Neptune's orbit and contains billions of icy objects left over from solar system formation. These objects consist primarily of frozen water, carbon dioxide, and other compounds. They remain completely frozen at the extreme distances from our current Sun. Our Sun's increased brightness during the red giant phase will send intense heat far into the outer solar system. Even distant Kuiper belt objects will experience significant temperature increases despite their remote locations from our dying star. Rising temperatures will cause the ice in these distant objects to sublimate directly from solid to gas. Sublimation is the process where frozen material turns into gas without becoming liquid first. The escaping gases form visible tails around the heated objects. This widespread sublimation will activate countless comets throughout the outer solar system simultaneously. The usually dark and invisible Kuiper belt will become a spectacular display of comet tails extending in all directions away from our brightening sun. Jupiter's large moons currently experience tidal heating from their planet's immense gravitational field. This process works like cosmic kneading that generates internal heat through gravitational squeezing. The moons stay partially warm despite their distance from our sun. Our sun's dramatically increased energy output will bombard the Jupiter system with intense radiation during the red giant phase. This external heating will add to the existing tidal heating and push the moon temperatures much higher than they experience today. The combination of tidal heating and intense solar radiation will cause widespread melting throughout the icy moon's interiors. Moons like Europa and Ganymede may develop extensive liquid water oceans beneath their surfaces. However, this heating will prove too extreme for maintaining stable conditions suitable for life. The intense radiation environment will make the Jupiter system lethally radioactive despite the presence of liquid water. Every planet with an atmosphere experiences weather patterns driven by energy from our sun. Temperature differences between day and night sides create winds. Solar heating drives circulation patterns that distribute heat around each world. Our sun's thousand-fold brightness increase will overwhelm every planetary atmosphere in the solar system. The extreme energy input will create temperature gradients and wind speeds far beyond anything these worlds have experienced in their histories. Atmospheric circulation patterns that have remained stable for billions of years will collapse completely. New circulation systems will develop under the extreme heating conditions. These new patterns will be chaotic and unstable compared to current weather systems. Planetary weather during our sun's red giant phase will become completely unpredictable and extremely violent. No existing climate models can accurately predict atmospheric behavior under such extreme energy input conditions. Earth's biosphere has survived multiple mass extinction events throughout geological history. Asteroid impacts, volcanic eruptions, and climate changes have eliminated most species many times. Life has always recovered and evolved new forms to fill empty ecological niches. Our sun's red giant transformation will create heat levels that exceed the survival limits of all known life forms. No evolutionary adaptation can prepare organisms for surface temperatures exceeding 1,000 degrees Celsius and the complete loss of liquid water. This represents what scientists call a sterilization event. Unlike previous extinctions that eliminated most species while leaving survivors, solar death will eliminate every living thing without exception. No recovery will be possible. The biosphere that has flourished on Earth for nearly 4 billion years will end permanently during our sun's red giant phase. This extinction will be absolute and irreversible under any conceivable future conditions. After our sun completes its transition to white dwarf status, the solar system will become a cold, dark place. The white dwarf will produce only a tiny fraction of our current sun's energy output. Temperatures throughout the solar system will plummet to near absolute zero. Any planets that survive our sun's red giant phase will become permanently frozen worlds orbiting a dim stellar remnant. These worlds will receive insufficient energy to maintain liquid water or any form of active geology. The white dwarf solar system will consist of dead, airless rocks orbiting through the cosmic deep freeze. No possibility for life will exist anywhere in this frozen graveyard of worlds. Our solar system's transformation from a vibrant collection of diverse worlds to a sterile white dwarf system represents one of the most complete environmental changes possible in the universe. Solar death means planetary death for every world in our cosmic neighborhood.